Okay, let's continue our discussion of equilibrium. I'm going to focus again on the Haber process that I mentioned in the last video, a very important industrial process. We're going to talk about these things called stresses. Now, stresses on an equilibrium are things like changing the concentration. We can do that by adding in a product or adding in a reactant. You can stress a system by changing the temperature, and you can also stress it by changing the pressure. Now I'm going to be reading some things from a website I found so I explain it very clearly. But the Haber process is a good equilibrium to discuss Le Chatelier's principle, which is what I'm focusing on in this part of the lecture. Le Chatelier's principle is a way to predict how an equilibrium is affected when you cause a stress on the system. So you can think of an equilibrium as a balance, a scale, so to speak. If you upset one side of the scale, it will shift in the other direction so that the balance is then reestablished. Now we're not going to treat this mathematically, even though you can. We just want to talk about it in general terms. How does the equilibrium shift when you cause different stresses on the system? So again, the Haber process, what it does is it combines nitrogen from the air with hydrogen. They usually get it from natural gas. And the balanced reaction has 3 moles of hydrogen plus 1 mole of nitrogen to give you 2 moles of ammonia gas. So pay attention to the physical states of the reactants and products in an equilibrium, because that will help you understand changes in pressure. Notice we have 4 moles of gas on the left and 2 moles of gas on the right. Also notice that you have heat written on the right, so this is an exothermic process. But in an industry, what they do is they recycle the ammonia. They recycle the reactant gases. They get ammonia produced and they remove it as it's produced, and that will shift the equilibrium to the right. The whole point of making ammonia is in industry is to maximize your yield in a reasonable amount of time. So they have to strike a balance between temperature, pressure, and so this is what we're going to talk about in this chart I have here on this page. How can we affect the production of ammonia? But I'm going to also ask you about how can we shift it not only to the product side, but how can we shift it to the reactant side? So they also use a catalyst to make this, to make NH3. I think it's an iron metal catalyst with some base added to it. Not so important that you know what the catalyst is, but understand how the catalyst, what it does in this process. So the catalyst does not affect the position of the equilibrium. It only speeds up how fast you reach equilibrium. That is an important thing to understand, because most people think when they're first learning this material that a catalyst is a stress on the system because you're adding in something. But a catalyst is not a reactant or product. It's a different molecule altogether. So you can only affect an equilibrium by actually adding in something that is taking part in the reaction. The catalyst essentially is just giving the hydrogen and the nitrogen a place to meet, a surface to meet, so the reaction will occur on a reasonable time scale. But what they really do is they combine the ammonia the nitrogen and hydrogen in a 3-to-1 ratio. They try to they want to have the reactants used up completely. They don't want to have any wasted material. If they do have wasted or unreacted starting material, it's going to be recycled back into the reaction anyway. When the ammonia is brought out of the reactor, they cool the mixture, which is going to be pretty hot. When they cool the mixture, the ammonia gas will liquefy, and the hydrogen and nitrogen will still stay as gases because their boiling points are very, very low, much lower than ammonia. So they'll stay as gases, and they can be recycled back into the reaction vessel and to produce more ammonia. So in an industry, the Haber process is, you can think of it as a cycle. So let's look at this chart and try to understand Le Chatelier's principle a little more. So let's say you add in reactants, and this is what they would really do in an industry. This is a change in the concentration. If you add in a reactant, you're upsetting the balance of this equilibrium, which is represented again with these red arrows. Adding in a reactant causes the left side of the equilibrium to have too much concentration, so the equilibrium will shift in a direction to minimize that. So it's going to shift to the right. That's really that's what you'd want to do. That's a good thing. It's making more ammonia. If you add in ammonia, all right, that would cause the shift to go in the opposite direction, toward the reactant side. So adding in a product shifts it to the left to form more reactants. Another way you could maximize the production of ammonia would be to remove it as it's formed. So removing a product is essentially the same thing as adding in a reactant. It causes the equilibrium to shift to the right. Removing, and vice versa, or conversely, removing a reactant, either H2 or N2, will cause the equilibrium to shift to the left. What about changes in temperature? Adding in heat. Think of heat as a product. So look at where heat is in this reaction. It's an exothermic process. So if you raise the temperature of this reaction, you're adding in a product, so to speak. That's why I put it in quotes. Raising the temperature would cause the equilibrium to shift to the left. That would not be a good thing for the company making ammonia. Too high a temperature would minimize the production of ammonia. But the problem they have is if they lower the temperature, lowering the temperature would cause the equilibrium to shift to the right. So that's an important thing to remember. If it's an exothermic process, as this reaction is, if you lower the temperature, you're going to cause the equilibrium to shift in a direction that will produce more heat, which is to the right. That's good. You would make more ammonia then. But the problem is if you lower the temperature too much, the reaction slows down to a crawl. It happens so slow that it wouldn't be worth doing it. So the industries had to come up with a way to say, okay, we need to run it at a temperature that isn't too high, but high enough that we actually get some ammonia produced. And so they had to have a balance between temperature and also pressure. I believe the temperature at which the reactions run at is about 400 to 450 degrees Celsius. That's a pretty high temperature, but not too high. It's high enough that you get some ammonia produced, and also it's high enough that it speeds up the reaction. Remember, increasing the temperature is going to cause the hydrogen and nitrogen to move faster and bump into each other more often, so the reaction will speed up, and that's a good thing from a kinetics point of view. They only get about 15% yield when they have the reaction run at 400 to 450 degrees, but 15% isn't too bad. Also notice that on the left side of the reaction, there are 4 moles of gas and only 2 moles of gas on the right. So you can also maximize the yield of ammonia by increasing the pressure. If you increase the pressure on this reaction, you're going to cause it to shift to the right. Now, why is that? It's because when you increase the pressure on this particular reaction, it's going to shift in a direction that's going to reduce the pressure. The only way you can reduce the pressure is to form fewer molecules per unit volume. So increasing pressure will shift it to the right, and that's what they want. They want to produce ammonia. So they run this reaction at about 200 atmospheres pressure, which is high enough that they can cause the shift from left to right to make ammonia. But the problem with high pressure is kind of the same that they had with high temperature. But they had to choose a a pressure that was high enough to make the reaction shift to the right, but not too high that the equipment costs got too expensive. When you have really high pressure reaction vessels and pipes and things like that, the company or the cost of the equipment becomes so high, it becomes so much that it isn't worth investing in. So they had to strike a balance between high pressure and high temperature, but not too high. So it took a fair amount of time for them to perfect this process. Again, this is this is probably the most popular way, or one of the most common ways that fertilizers are produced in this country. Notice adding in a catalyst does not cause a shift in the equilibrium. It only speeds up the formation of the ammonia gas. So to summarize, Le Chatelier's principle, Le Chatelier is a French name. He was a French scientist who did a lot of work with gas phase reactions like this. So they named it in his honor. If a chemical system at equilibrium experiences a change in concentration, which we can represent with these square brackets, temperature, volume, or pressure, then the equilibrium will shift to counteract the imposed change, and a new equilibrium is established. So we can also look at, I had this slide up, or this diagram up earlier in the other video talking about what equilibrium is, but we can talk about Le Chatelier's principle as well for what's called an endothermic reaction like this one. This is an exothermic reaction, so raising temperature here is going to cause it shift to the left. Increasing or decreasing temperature will cause a shift to the right. The opposite is true for an endothermic reaction like this. If you have water in a closed container, it's going to eventually reach an equilibrium where the rate of evaporation is equal to the rate of condensation. But it takes energy to cause the water to evaporate. So that's why for an endothermic reaction or equilibrium, the heat is on the left. So raising the temperature will cause the equilibrium to shift away from that stress, and it will shift to the right. Problem with shifting to the right is you increase the pressure because you're increasing the production of water in the gas phase. So that would cause this pressure to rise. But that's what a pressure cooker is. You increase the internal pressure inside by covering it, and you can cook things faster. That's the point of using a pressure cooker. But keep in mind that an endothermic equilibrium behaves in the opposite way to temperature versus a exothermic reaction. So to summarize what we've been talking about here, you can cause an equilibrium to shift by adding in products or reactants. If you add in a reactant, you upset the left side of the equilibrium, so it shifts to the right. Notice the size of the equilibrium constant is not affected. That's important. It doesn't cause the equilibrium the position to shift after it's reestablished equilibrium, so K doesn't change. But these stresses will cause a temporary shift in equilibrium, and then a new equilibrium is established, but the equilibrium constant itself is not affected when you add in products or reactants, or if you change the pressure by either decreasing volume or increasing volume. As in the Haber process, if you increase the pressure on the system, you're going to cause a shift to the right side, which is the ammonia side. That's why I have it written here, shift to fewer gas molecules. If you have a equilibrium that has more gas molecules on the right, then increasing pressure would actually shift the equilibrium the other way, would shift it to the reactant side. So do some homework problems or some textbook problems to help you solidify this concept a little bit better. You can also, if you have if you increase volume or by decreasing pressure, or vice versa, you decrease pressure by increasing volume, you shift to the side that has more gas molecules. You can cause a shift in equilibrium, as I've said, by increasing temperature or decreasing temperature. So in the Haber process, again, increasing temperature, you're adding in a product, you're going to cause an equilibrium to shift to the left. You decrease temperature, you're removing a product, so to speak, so you cause the equilibrium to shift to the right. So I would also like to talk about these concepts of equilibrium, discussing what are called weak acids and strong acids. So earlier on in the course we talked about strong acids being things that essentially 100% ionize in solution. So hydrochloric acid, for instance, when you throw it into water, 100% of the molecules break apart, dissociate, or ionize. Versus a weak acid, this formula here you might recall is acetic acid, the main ingredient in vinegar. That is a weak acid. A weak acid is something that doesn't ionize very much, maybe about 5% of it or less breaks apart into protons and the conjugate base. So weak acids are reversible, and strong acids are not. Strong acids are essentially reactions that go to completion. So what is an acid? Again, we talked about this before, but it's a molecular substance that increases the concentration of the protons in water. So this is how we'd represent the dissociation of HCl or nitric acid or H2SO4 in solution. It's not an equilibrium mixture. It's just written left to right. So keep in mind that most reactions are equilibria, the plural, but even strong acids. But if they're almost 100% complete, we usually just write it as a left to right arrow. So this diagram here, we can represent visually the difference between a strong acid and a weak acid with this picture here. If you add in 4 moles of HCl, for instance, you would get 4 moles of each of the protons and 4 moles of each of the chloride ions, represented here as A-. So that's your 100% dissociation. A weak acid, on the other hand, we need to represent with an equilibrium because most of the molecule does not break apart. Only a few percent of the HA molecules ionize. So we represent those two different situations in slightly different ways. Make sure this is straight here. There we go. HCl, you can represent the dissociation of HCl like this. The bond breaks, you get a proton and a chloride ion, and we write water there as it's not a reactant written in this way. But in reality, it actually is a reactant. This is a reaction. It's an acid-base reaction. This is the base in this case, and this is the acid. So this is the other way to represent the dissociation of HCl. What's going on is a water molecule is actually pulling off a hydrogen from HCl, and you're getting the conjugate base of HCl, which is the chloride ion, and then you get this kind of strange looking thing, but all it is a water molecule with an extra hydrogen attached to it, so it has a positive charge. That's called the hydronium ion. But a lot of students find this way easier to think of strong acids dissociating. You can actually use this simple version, this simplified notation for weak acids as well. And that's what I've shown you here. So contrary to strong acids being written as just a left to right arrow, we have to represent weak acids dissociation, ionization, whatever you want to call it, with an equilibrium double-headed arrow. So this is an acid called formic acid. It's, I believe ants actually excrete this acid as a defense mechanism. It's the simplest organic acid. It only has 1 carbon. This acid here is, you probably recognize as the formula for acetic acid, which we can draw in a few ways. I've drawn them out in the Lewis structure here just to show you the difference between the two types of hydrogens. This hydrogen here is the acidic proton, we say, the one that's attached to the oxygen. These hydrogens over here in formic acid or acetic acid are not acidic. They never leave the molecule. They always just stay bonded to the carbon because that's such a strong bond. But an oxygen-hydrogen bond is relatively weaker, and that is the bond that breaks when you have these acids breaking apart. So this behaves as an acid, as does this by this bond breaking, forming protons in the solution and the conjugate base. So in a week or two, when we talk about weak acids and bases, acid-base chemistry, and I ask you, we talk about pH of a solution. What we're talking about is how many protons are in the solution. What's the concentration of the protons? That's what pH is. So in reality, we should really represent these equilibrium, these dissociations, as this sort of double-headed arrow, not as an equally sized double-headed arrow, but a double-headed two-directional arrow like this, but the left arrow is a lot larger than the right. Why? Because by this notation, we're expressing the fact that the equilibrium lies to the left. If you were going to think of this as an equilibrium, you would actually draw a very, very tiny arrow to the left. So a strong acid might still be considered an equilibrium, but it lies so far to the right that the value of K is so large, we say it essentially is 100% ionized. Weak acids, by contrast, we have to represent like this or like this, which means that the value of K is very, very small, much less than 1. So that's the mathematical difference between a strong acid like this and a weak acid. The size of the equilibrium constant, very large for strong acids, so large that we almost never express or even state the value of K for HCl. It's a number, probably 1,000 or 10,000. It doesn't really matter. But we do need to express these weak acid equilibria with a value of K. And the main reason is because when we calculate the pH of a solution, if it's a strong acid, we don't need to do we don't need to use the quadratic formula. We can just say that the moles of the protons equals the moles of the acid that we threw into the solution. So it's a 1-to-1 ratio essentially. And we can say that because if it breaks apart or 100% of these ionize, then we can say moles of HCl equals moles of H+. That makes the pH calculation very easy. If we were trying to figure out the amount of protons formed in a weak acid equilibrium, it would be much more difficult. We cannot say that the moles of protons is equal to the moles of acid. Therefore, we have to do some more complicated math. We're going to try to treat acid-base chemistry in a little bit more simple way than that, though. But just keep in mind at this point that the value of K is much less than 1 for a weak acid dissociation. So we have a special way of writing the value of K. Notice here I just wrote it as KEQ, or just K without a subscript. That's what we do. We choose different subscripts on K depending on if we're talking about a run-of-the-mill equilibrium, like the production of ammonia from its elements, or if we're talking about an acid or a base. For acids, we use this subscript A. It's called the Ka. So this just represents the dissociation of some weak acid, and it gives up 1 proton to the solution. We call this the proton donor, the base, the proton acceptor. So again, a weak acid can go in either direction, and actually it does. There's a competition between the reactant side and the product side. But when we express the value of K sub A, Ka, it's still the same as any other equilibrium constant. It's the product concentrations on the top, the reactant concentration on the bottom. But remember, when you write an equilibrium expression, you multiply the concentrations of the products. You don't add them up. It's a product. It's multiplication. And so the size of K being small should make some sense to you at this point, because if a weak acid is a weak acid because very few of these molecules breaks apart, then it makes sense that the value of Ka is very small, much less than 1. Just think of it this way. Let's say you have 100 molecules of acid. Out of every 100, if it's a weak acid, maybe 1 to 5 of the acid molecules breaks apart into H plus and A minus. So if you have one of these and one of these formed from 100 of those, you have essentially the number 1 in the numerator and the number 99 or 100 in the denominator. So you have a very small number divided by a very large number. Therefore, you have a number value of K that's much less than 1. So that's how we represent the strength of an acid. We don't generally write the value of K for strong acids like HCl or HNO3 or H2SO4. K is very large. We don't really care what K is because we're assuming that 100% of the acid ionizes, so we can calculate the pH of the solution without considering K. But we have to consider K when we talk about weak acids if we want to get the pH of the solution. So again, this is what you'd see normally in a textbook or in a chart. You'd see these Ka values listed. This is formic acid again. Its value of Ka is very small. It's 1.8 times 10 to the negative 4. I've written it in normal notation there. Acetic acid, we say, is 10 times weaker than this one. So its Ka is actually 1.8 times 10 to the minus 5th. So even though that's a very small number, this acid is 10 times stronger than this one because of the size of the Ka. So that's what I want you to understand at this point is, looking at relative sizes of Kas, can you predict the relative strength of weak acids? And we can also apply this same logic to weak bases. I hope that was clear for you. You might want to go back, rewind, and watch some of these videos again.